Okay, we are extremely pleased to have this time Professor Moffatt, FRS, from his home place in Cambridge. And we are going to, I'm sure, to have a beautiful review of some topological aspects of fluid dynamics from the Helicity man himself. Keith, to you.
Well, thank you, Renzo. And hello, everyone. I'm very glad to be invited to give a lecture in this great GEOTOP series. As I think you all know, topology and fluid dynamics do have a very natural symbiosis in that both are concerned, at least to some extent, with continuous deformation, with properties that remain invariant under such deformation, and with processes that can alter topology, sometimes through singularities. So in this lecture, I shall endeavor to cover at least some of these aspects. So here's the rough plan. I'll start with a little bit of historical background that may be already very familiar to all of you, and then some words about critical points and singularities, and then I'll have a pause for questions, and then I'll talk about frozen-in fields and dynamo theory, and then possibly another pause, but perhaps not, time may not allow. Then relaxation under topological constraints, and finally the notorious finite time singularity problem. If I don't have time to cover all this, then be assured that there is a paper in press at the moment in JFM, which I hope will appear soon in the Perspectives series. So here's the bit of history. These are four great scientists of the 18th century who we can hold responsible to some extent for this subject. The first is Helmholtz, who published his paper in 1858 on the laws of vortex motion. 3 laws, one of them actually wrong for reasons that I'll come to. But the third law is the one that concerns us most in this subject, the fact that vortex lines in fluid flow, vorticity being the curl of the velocity field, vortex lines are transported with the flow. Sometimes we say they're frozen in the flow field. Well, Kelvin was very excited about this result of Helmholtz, and it led him to propose his vortex atom theory in 1867, explaining the atomic, or seeking to explain the atomic structure of matter in terms of knotted vortices in a hypothetical ether. This in turn led Tate, Peter Guthrie Tate, in the 1870s to initiate the classification of knots of crossing number from 3 up to 10. There was a very lively correspondence between Tate and Maxwell. They were close friends since their school days together in Edinburgh, and some of that correspondence is really very interesting. Here's a letter from Maxwell to Tate, the first page of a 4-page letter. You see, he writes from his estate in Glenlair in the southwest of Scotland. He requests in this letter a copy of Tate's translation of Helmholtz's paper of 58. This letter is dated 1867. And then he explains how he had set some of what he calls Helmholtz dogma for student exams in 1866. That's before the paper, well, just as Tate was translating the paper from German to English. He says that they had solved it completely as to the calculation and nearly as to the interpretation. Evidence that Maxwell was very much, well, as much concerned with physical understanding of his results as with the mathematics. Then he goes on to say that Thomson, that's Lord Kelvin later, has set himself to spin the chains of destiny out of a fluid plenum. And I saw that you, as Tate, had put your calculus in it too. May you both prosper and disentangle your formulas in proportion as you entangle your warbles. Warbles was Maxwell's term for vortices. I think the word vortices had not quite entered the literature of the language of the subject at that time. Tate would normally reply on a postcard. Here you see one from a little later, 1872, but on the other side there was always dense scientific arguments, and that was the way they communicated. This postcard cost 1/2 penny, and that's a half old penny, about 0.1 of a new penny. Well, to come to a little bit of serious mathematics, as I say, there's a natural symbiosis between fluid dynamics and topology, both being concerned, at least to some extent, with continuous deformation. Here's an interesting example, I think. These pictures show streamline evolution of a two-dimensional flow with a stream function, psi, function of x, y, and t. So it's unsteady, y squared plus x cubed minus 3xt. The velocity is two-dimensional. The velocity components, d psi by dy and minus d psi by dx. So it's an incompressible flow. The streamlines are the contours psi equals constant. For t less than 0, for t negative, there's an extremum at this point, x equals minus t to the 1/2, and a saddle point at x equals plus minus t to the 1/2. So here they are. Here's the x equals 0 up here somewhere, the elliptic point here, and the saddle point here. As t increases towards 0, these 2 points approach each other, and they merge at t equals 0 in what is actually a degenerate stagnation point, where the streamlines are cusped at this point instantaneously. But for t greater than 0, it smooths itself out again. Now, the interesting thing is that since you have them separated by 2 times minus t to the 1/2, they are approaching each other with a velocity proportional to minus t to the minus 1/2, and therefore they actually merge at infinite speed, although the velocity field is everywhere perfectly smooth. And that strikes me as rather intriguing. It's a property, I think, a generic property of evolving two-dimensional flow patterns, the sort of thing that one sees always with evolving meteorological maps on our television screens. In general, if in a bounded, simply connected domain with psi equals 0 on the boundary, imagine this sort of flow but closing, so psi is 0 on a larger boundary, there are NE extrema, or elliptic stagnation points of this kind, and NS saddle points, then NE minus NS is a constant equal to 1 in this case. This is Euler's theorem, and it's a very basic topological result. You might say the most elementary topological result in fluid dynamics, with application to it has many other applications, of course. Here's a slightly more complex situation that I was very much involved in the early 1960s, flow in a corner. Now here, the boundaries are no-slip, rigid boundaries with fluid in the angle here. So one is in a way imposing a singularity on the boundary. But if you drive a flow by any means, for example, by a rotating cylinder here, and this is a viscous fluid, then this is what the solution of the Stokes equation looks like. That solution has the form, again, of a stream function, r to the power lambda times a function of theta in plane polar coordinates satisfies the biharmonic equation in the Stokes approximation, very viscous flow, which is always valid very near a sharp corner, and with no slip boundary conditions on the two boundaries, theta equals alpha, theta equals minus alpha. Well, these equations, I needn't go into the detail, but they lead to an equation which determines the exponent lambda, sine 2 mu alpha equals minus mu sine 2 alpha, where mu is lambda minus 1. And what is interesting is that the relevant roots of this equation, relevant being mu greater than 0, are complex. They're all complex if the angle 2 alpha, the total angle, is less than 146 degrees. And complex exponent here implies infinite oscillations as r tends to 0. See, if lambda is p plus iq, then you've got r to the p, e to the iq, which is like cos q log r. And as log r goes to minus infinity, you get these infinite oscillations. Now, you might say, well, there's many elliptic points, but where are the saddle points? Well, they're all on the boundary, in a sense. Half of a saddle point is here, for example, and the other half is here. So for every elliptic point, there are two half saddle points. So each contributes a half to the number ns, the number of saddle points. So Euler's theorem is valid with this qualification about boundary saddle points. Here's a different kind of singularity, which is even more interesting, I think. Here I have a bath. This is an actual experiment, a bath of golden syrup, very viscous fluid, edible fluid. Two cylinders immersed, which are rotating, and they're rotating, this one rotating clockwise, this one anti-clockwise, so as to draw the fluid towards the plane of symmetry. And the fluid dips downwards here when they're rotating rapidly enough and seems to form a cusp. This is an idealization, a model problem that represents this, using a vortex dipole here of strength alpha to represent the same type of flow, drawing the fluid down towards what looks like a cusp. Although if we look very, very closely at this, zoom in, we'll see that it isn't quite a cusp. It's slightly rounded with radius of curvature, capital R. Now that radius of curvature is extremely small, as evident in the picture, but we can solve this problem exactly as a problem using conformal mapping. And analysis shows that the ratio of this R to D, the depth of the dipole below the undisturbed surface, that ratio works out as 256 over 3 times the exponential minus 32 pi times a number c. C is just mu alpha over gamma d squared. Mu is viscosity, gamma is surface tension. So effectively this is a ratio of the viscous force, which is pulling the surface down, to the surface tension force, which is in some way resisting this action. Now, if you have a level playing field, C equals 1. The two forces, let's say, are in some kind of equilibrium. Then R over D, C equals 1 here, we can work it out. It's an extraordinarily small number, which merits these 3 exclamation marks. 1.87 times 10 to the minus 42. Well, if that's, say, 10 centimeters, which is roughly what it was in the experiment, then R will be less than the radius of the proton. So it's a bit unrealistic. Well, it's totally unrealistic. It means that some other physical mechanism must actually resolve this incipient singularity. And what resolves it is that air is drawn through the cusp in such a way as to resolve it. You can see that little streak of black here. That's actually a very thin layer of air which is drawn through the cusp, and forms another bubble here, a sort of tent-shaped bubble, and little bubbles are shed into the fluid, and then they can be observed circulating around the cylinder. I've tried to exaggerate this here with bringing the two cylinders together. There is the thin sheet. One might be able to solve this problem by lubrication theory with a thin layer of air, which again opens out into a bubble of rather interesting shape. The bubble is being pulled down by viscosity, but it's trying to rise by buoyancy, so it achieves roughly an equilibrium configuration. Now, the funny thing about this problem is that if you were just to use dimensional analysis, you would come to the conclusion that d over r must be some dimensionless number of order unity. And it is. It's a dimensionless number. And this is, in a sense, it doesn't depend on any small parameter. It's a number of order unity, but it's the smallest number of order unity that I have ever seen emerging from a fluid dynamical problem. Comment concerning small numbers of this kind. If you take the gravitational attraction between two electrons, the ratio of that to their electrostatic repulsion is likewise an extremely small number. And Richard Feynman commented on this in his famous 1963 lectures. He said this: "Someday, some say that we shall one day find the universal equation, and in it one of the roots will be this number. It is very difficult to find an equation for which such a fantastic number is a natural root." Well, for our cusping problem, there's no small parameter in the statement of the problem, but an extremely small number emerges from its solution. So there is perhaps an indication that someday a number of this kind may emerge in theories of unified field theory. I'm not claiming that cusping has anything to do with unified field theory. Now I'd like to say a few words about a related problem known as the Herculean paradox problem. You may know that in Greek mythology, it is said that Hercules dipped his arrow in the venomous blood of the Hydra. This was one of the great labors of Hercules, which you see illustrated here. He had to kill the Hydra, and it was quite a problem for him, as you can see. However, having completed it, he dipped his arrow in the venomous blood of the Hydra. Now we can model that as shown here. Imagine a fluid here, the blood of the Hydra, and a plate that is drawn in, modeling the arrow of Hercules. This is a two-dimensional version. Free surface here. There is a solution of the Stokes equations of the form psi equals u r times a function of theta. However, that gives a viscous drag on the plate that is singular at this point here, assuming that the free surface remains horizontal. It's a 1 over r singularity, but that is non-integrable as r goes to 0. So the force required to push the plate downwards would be infinite if this were the correct solution. Not even Hercules could achieve this feat. However, the free surface is in fact dragged downwards a little bit when the plate is in motion. And if we assume that it meets the plate now at a 0 contact angle, then we can use the cusp solution that we had before. And for that cusp, of course, this is just half of the cusp, which would continue here. But the singularity for that solution is in fact like r to the minus 1/2 as r goes to 0 at this point here. And this is now integrable, so that the force required to push the plate downwards is finite. And in this way, the Herculean paradox, as it's called, can be resolved. Now, let me say a word about Lagrangian chaos in three-dimensional flows. The first example being the famous ABC flow, whose velocity components are shown here with these coefficients A, B, and C, although in fact they stand for Arnold, Beltrami, and Childress, who all contributed in very significant ways to this problem. For this particular flow, the vorticity omega, the curl of U, is actually equal to just K times U, as you can very easily verify. This is what makes it a Beltrami flow. This is a space periodic steady flow, and it can be thought of as a flow on the 3 torus T3, first studied actually by Arnold and Henon. These pictures show sample Poincaré sections, which show points where a single streamline crosses a particular plane of section. And you can note the islands of regularity in a sea of chaos, particularly here. Here are the islands of regularity and sea of chaos, where there's a great scattering of points. This is for 3 values of A, B, and C that are very far, well, unequal. Here they're all equal to within plus or minus 1. And you can see that the chaos is much reduced when you go from here to here. I don't know if that the reason for that is fully understood. But the problem is very thoroughly studied in the paper by Dombre et al. In 1986 in JFM. Another example is a steady 3D flow, this time in R3 inside a sphere, a velocity that has 3 ingredients, U, V, W. U is like a Hill's vortex inside a sphere, pointed in the direction of the vector A. V is rigid body rotation in the sphere, and W is a superposition of 3 twists. The coefficients lambda, mu, and u have to sum to 0 to keep the flow inside the sphere. The streamlines for a particular choice of all the parameters here are shown in this picture, and it looks like 2 primary vortices. And you might think that that streamline lies on a surface, but in fact it doesn't, because when the streamline passes through either of these points, which are actually stagnation points on the spherical surface, the streamline shifts just a little bit, or the surface shifts just a little bit. And when the Poincaré section is done through a section of the diametral plane of the sphere, and the streamline is followed a large number of times, here 40,000 times, you see again the scatter of points indicative of chaos. Any questions at this point on any of these topics that I considered? You remember the transition here when a saddle point coincides with an elliptic point. Here the cusp singularity, and here the chaos, flow with chaos. Here the infinite number of the infinite singularity at a corner. I pause for a moment in case there are any questions.
Well, Keith, if I may, you mentioned your work on cusp formation, and I wonder, we are facing usual problem when we think of the role of topology and the associated problem of the singularity formation in, say, Navier-Stokes, etc. You worked on these aspects too, and I'd like to hear a comment from you. Evidently, when we think of a way to get an inverse from the flow map, this must have to do with the shear stresses. And shear stresses must account for a way to reconcile initial conditions to final conditions. Do you see a way from all this work that would be able to reconcile these two conditions?
Well, it is indeed the shear stress that pulls in this case, when the two cylinders are close, shear stress is what pulls the fluid down and is instrumental in forming the cusp. But one might ask also, and I think your question has a bearing on it, what has it to do? Well, in a way, how is the singularity resolved? I mentioned that this is to do with the air being drawn in, again, an effect of shear, drawn in a very, very thin layer and forming another bubble, an air bubble down here. That still doesn't actually change the topology of the free surface, but little bubbles are ejected from these points here into the fluid, and it's actually there that the change of topology of the free surface takes place. Funny enough, I think you can see one or two little bubbles right here, but they are emitted from these regions into the fluid. So it is all to do with shear stress. Viscous stresses resisted by surface tension, but when the viscous stress overcomes the surface tension, then the topology of the free surface does change.
Mm-hmm. Thank you.
Well, let me continue to the next topic, and that concerns transported or frozen in fields. I'm always considering a volume preserving velocity field satisfying div(u) equals 0. If you have a scalar field, for example, temperature, or it could be just a colored dye injected into the fluid, then the concentration of that dye satisfies the passive scalar advection diffusion equation. There's a minus u dot grad theta, that's advection, sometimes written in terms of a Lie derivative, the derivative of theta following the flow, plus a diffusion term. And if that diffusion coefficient kappa is 0, then the surfaces theta equals constant move with the fluid. And as a result, grad theta increases in general on average and in magnitude as these surfaces are deformed, really because the area or the volume between two surfaces theta equals constant is conserved, but their area increases. For a vector field, it's a little more complex. Here I'm thinking of a solenoidal vector field, div b equals 0, and the prototype example is magnetic field in a conducting fluid, which satisfies what is known as the induction equation here. This is now the advection term that corresponds to frozen in field, but there can also be a diffusion, ohmic diffusion with a constant eta here. And again, this is the Lie derivative, the derivative of b following the flow u. And if eta is 0 here, then the b lines move with the fluid and are stretched on average. In this way, flux tubes are similarly stretched, and the field intensity is correspondingly intensified. It's very like the tension in a stretched elastic cord. And this, in fact, is the essence of dynamo action that we'll come back to in a moment. Here are two examples of field line distortion. The first is a cranking distortion, or in fact, it's a form of differential rotation. If you think of a magnetic field line in blue along the x-axis, and you grip it at the center and wind it round the x-axis, then this is the resulting deformation. So it's as if the field line is gripped and cranked round the axis. The second deformation I describe as omega twisting. Here it's as if the field line is locally lifted to an omega shape locally, and at the same time twisted round the z the z-axis here. Here I've got x and y and z upwards. For this type of distortion, the velocity u and the vorticity omega are roughly locally parallel. Certainly u dot omega is non-zero. Well, that has a bearing on what we know as helicity. For a general fluid velocity u, a function of position x and time t, which may be random if the flow is turbulent, the vorticity omega is the curl of u, as we've had. The helicity h is u, the scalar product of u and omega, and it is usually the average, sometimes the integral of this quantity, sometimes the average for a turbulent flow. The correlation between u and omega, and this is a pseudo-scalar, a very important property. It can be non-zero even in isotropic turbulence, invariant under rotation. Think just of a box of screws that is vigorously shaken. If all the screws are right-handed screws, then you still have a helicity, even if the orientation of the screws is quite isotropic. The flow is right-handed if h is greater than zero, left-handed if less than zero, in a right-handed coordinate system. Well, it's an important concept because it turns out to be an invariant, constant in time, an invariant of the Euler equations of fluid mechanics, ideal fluid mechanics, a result first found by Jean-Jacques Moreau in 1961. It's a measure of the conserved degree of linkage of tangled vortex lines and therefore certainly topological in character, as I discussed in my paper in 1969. In a way, it's just the sort of result that Kelvin needed in his consideration of vortex knots. This is also something we'll come back to. Well, there's an invariance property, as I've mentioned, most easily proved for a magnetic field, the magnetic helicity invariance, for any field that is a frozen-in field. For a magnetic field, let's put eta, the diffusivity 0, b, the curl of a vector potential, and hm, the integral of a dot b. B is the analog of vorticity, a then the analog of velocity. So this is like the integral of u dot omega over a domain D. Well, D has to be a Lagrangian domain with b dot n 0 on its surface. That's a magnetic surface which moves with the fluid. Well, B, I've written the induction equation in a slightly alternative Lagrangian form here. Capital D by dt is the Lagrangian or material derivative, and the corresponding equation for vector potential is written here, where this is the transpose of grad A, and phi is an arbitrary gauge for the magnetic vector potential. Again, div-u is 0, although in fact this condition is not necessary for this type of proof. The rate of change of this integral has two terms, a dot dB by dt, b dot dA by dt, and the volume element is conserved under this condition. So we can manipulate this using these two equations and turning it into an integral over the domain of this form, b dot grad of a scalar, and that is immediately transformed to a surface integral b dot n, the same scalar, which is 0 by virtue of this condition on the surface. So hm is indeed a constant. It's a fundamental topological invariant of any divergence-free transported vector field. And as I say, it's true also for flow in a compressible fluid, but I want to give the modified proof of that. This proof, well, Vulture 1958 is frequently referred to. He gave an earlier, less general version. Now, it's also, as I've mentioned, an invariant of the Euler equations. Here, vorticity is the curl, and it's the frozen-in field. Euler evolution, if viscosity is 0, So now h, the integral of u dot omega, is constant. It's a measure of the degree of linkage and or knottedness of the vortex lines in the domain D. Now, the omega dot n has to be 0 on the surface. And these are two relevant references. Well, now let me come back to dynamo action and also magnetic relaxation, which I see as complementary processes for the following reason. Here again is the frozen field equation if eta is 0. Let's here suppose that B is a localized field in an infinite fluid. With current J equal to the curl of B, the rate of change of magnetic energy, which I've taken here, integral of a half B squared dV, the rate of change of that can be written, very well-known equation, as minus the integral of U dot J cross B, this is the Lorentz force in the fluid, minus eta integral J squared dV. This is the remorseless decay of magnetic energy due to ohmic dissipation. This term here, however, is what interests us. For a dynamo, U dot J cross B has to be negative on average. With this minus sign, that makes this term positive, and magnetic energy can potentially increase. The fluid must push against the Lorentz force on average. For relaxation, by contrast, U dot J cross B is positive on average. In other words, the Lorentz force drives the fluid. If this Lorentz force, it pushes the fluid in the same direction on average. It's got to be, I've got to say on average, because div U is 0. It's got to be maintained 0, and divergence of J cross B is in general non-zero. But for this reason, we should regard these as complementary processes. Well, now, helicity. In the 1960s, there was a breakthrough, which we now recognize as mean field electrodynamics, which gives in a turbulent flow what's known as the alpha effect, a mean current that is proportional to the mean magnetic field. It's a great surprise, really, because in Maxwell's native equations, there is no such term. J is, if anything, it is perpendicular to the magnetic field through the U cross B effect. But here there is an average effect, and this alpha turns out to be very closely related to the helicity of the turbulence. There were precursors of the theory from Parker in the 1950s and from Braginsky in Moscow the early 60s, but the theory developed dramatically by Steenbeck, Krause, and Redler in 1966. And what is, well, the essence of this effect is indicated here by this diagram. If you take the omega twist type of flow, in other words, a rising twisting with U parallel to vorticity. So H is certainly, as I've shown it here, greater than 0. It is this type of flow that gives rise to the effect if elements of this kind are randomly distributed over the field of flow. And the result is this: if H is non-zero in a sufficient expanse of conducting fluid in turbulent motion, then a large-scale magnetic field will grow spontaneously from an infinitesimal level. In other words, order in the form of the large-scale magnetic field emerges out of the chaos of the small-scale turbulence. This is a very dramatic result. It's one of the, I believe, most significant results, theoretical results, to emerge from turbulence theory in the last half century. And the Earth is certainly large enough. H is non-zero because Coriolis forces conspire with turbulent convection in the liquid core of the Earth. This is an artist's representation of the flow. It's why the magnetic axis ends up so near, not coincident, but so near to the rotation axis of the Earth. There's a sort of input scalar, gravity dotted with rotation, which is non-zero, changes sign across the equatorial plane, but over a sufficient volume of fluid, it is non-zero and of constant sign. And that is why the geodynamo operates. As I've shown here, H is positive in the northern hemisphere, negative in the southern hemisphere. There is the solid inner core, but then the liquid outer core. This is the Earth's solid mantle, and we are some distance away. This is the idealized schematic of flow in the liquid core. This is a numerical simulation, the first successful numerical simulation by Glatzmeyer and Roberts in 1995, who also found polarity reversals. Well, in the liquid outer core, the lines of force are convected and diffused in the fluid, leading to self-exciting dynamo action. Outside the Earth's surface, the field is approximately dipolar, as you see far out here, an approximately dipolar field as we observe at the surface of the Earth. It's even more amazing that the same dynamo mechanism operates in all self-gravitating, rotating celestial bodies with conducting fluid interiors. In other words, most other planets, the Sun, stars, and galaxies. The stars and galaxies being regarded as fully ionized gas or plasma, the plasma term more familiar in the controlled diffusion context. Here's a picture of the Sun where you see prominences from the Sun extending to the solar corona, following generally the lines of force of the external dynamo-generated magnetic field. Here's the surface magnetic field of a young star, imaged by Zeeman Doppler imaging, plus some creative, image processing. The same applies to spiral galaxies. These are magnetic fields measured by various astronomical techniques in these or around these spiral galaxies. Here's our own galaxy, the galactic disk, with a strong magnetic field within the disk and a weak magnetic field in the external halo of the disk. This effect, dynamo effect, has been realized experimentally in Cadarache, the site of the Centre Énergie Atomique in France, in what's often described as the washing machine, two counter-rotating propellers in a large container of liquid sodium, highly conducting liquid sodium, and highly inflammable. So it's a massive experiment in turbulent flow, copper cylindrical container about the size of a washing machine. As the speed of the propellers is gradually ramped up as here, then at a critical value, a magnetic field is observed in probes that are located at the boundary of this container. And that is believed to be an alpha-omega type of dynamo, in which the alpha effect operates in the turbulent flow in the interior, and there's also a differential rotation effect, like an omega effect, due to the differential rotation of the two propellers. Another dynamo mechanism, very well known, the stretch, twist, fold mechanism, is like stretching an elastic band. Here's a tube of magnetic flux, stretched, twisted, and folded. If you have flux going around phi here, then the total going around here is 2 phi, phi in each of the twisted bands of flux. But at each stage, both writhe and twist are generated in such a way that the sum of these is constant. This is actually a manifestation of helicity invariance, because for this type of situation, the magnetic helicity is proportional to h to phi squared, the flux squared, with a constant, dimensionless constant here, h, which is just the writhe plus the twist. This is a paper that Renzo, Rika, and I published in 1992, establishing this identity. Another great bridge between fluid mechanics on the one hand and, well, here differential geometry, but also with a topological character on the other. Here's a fast dynamo, the Galloway-Proctor fast dynamo, for which the velocity field U has these components. It's rather like ABC flow, with B and C, I think, both equal to 0, but also time dependent, with periodic dependence on time. You have the sine t, cos t, sine t, cos t in each component. Well, the structure of the fastest growing magnetic mode is shown here in the picture. It's almost 0 in these regions. It's non-zero only in very thin layers, which are roughly proportional in thickness to magnetic Reynolds number to the -1/2. Magnetic Reynolds number here is simply A over eta. A is the coefficient here. The dimension, well, length is non-dimensionalized in terms of the size of the box. So the field is extremely sparse. The RM for this picture is 2000. RM to the -1/2, well, it's thin. As RM goes to, well, increases further, these layers get thinner and thinner, and they vanish altogether in the limit. So you just would not see the field. There's serious existence problems in general for what are known as fast dynamos of this type. This is all described in Galloway's paper, reviewing the field in 2012. Well, let me turn now to magnetic knot relaxation, which relates to a number of earlier lectures in this series. Imagine we start at time t equals 0 with a knotted flux tube, or it could be a linkage as shown here, in a perfectly conducting fluid, but viscous, nu greater than 0, eta equals 0, incompressible, in some domain D, now a finite domain. Let this relax under the action of the Lorentz force. Remember, the Lorentz force now in relaxation pushes the fluid, so it drives the flow and transports the magnetic field, so HM is constant in particular. For as long as the fluid is in motion, energy is dissipated by viscosity, so the energy decreases. It attains a minimum only when U is equal to 0, and this minimum is governed by an inequality stated by Arnold here, in terms of magnetic energy on the right and magnetic helicity conserved on the right. LD is the length, the scale of the domain within which this is contained. For example, the trephine knot will relax in this way. It relaxes really because the tension, the magnetic Maxwell tension in the tube causes the tube to contract in length. But because it's incompressible, in an incompressible flow, the cross-section must increase. So it's something like this, shown schematically. And ultimately, the length is of order velocity, volume of the tube to the 1/3, and the area is of order volume to the 2/3. So these are the two constants, flux and volume, but also the helicity. So the H parameter here is constant. And on dimensional grounds, the ultimate magnetic energy must have the form m of H. some dimensionless function of this dimensionless variable times phi squared v to the minus 1/3, this having the dimensions of energy. Well, there may be more than one ultimate state. It's by no means necessarily unique. For example, for the trefoil knot, here's an alternative initial geometry, the same knot, but it will relax to a different configuration with a different minimum energy. So we should really imagine a series of these functions, which we can describe as the energy spectrum of the knot, with the smallest energy having, well, we describe this as the, if you like, the fundamental energy configuration. Same sort of theory can be applied to braids, and there's a lot of work going on in this area. Here we think of a field that runs from one perfectly conducting boundary to another, and then we imagine moving the foot points of the field in some random manner on these boundaries, so the field becomes tangled in the interior and then allowed to relax. And Parker has written a whole book on this topic, Spontaneous Current Sheets in Magnetic Fields, in which he shows that in general one must anticipate current sheets where the field lines tend to come into coincidence. Here's an idealized geometry again of two simple flux tubes. So an initial configuration in which the red tube is wound round the blue tube in a helix, partial helix, but wound round through 2 pi degrees, allowed to relax. It wants to become more straight, but it must meet the blue tube in a field of discontinuity. The blue tube will deform a little, and it depends on the relative strength of the two tubes how much this deformation will be. It's twisted by an angle greater than pi by 2 around the blue tube and allowed to relax. Greater than pi by 2 implies that there will always be such a discontinuity forming. Here are actually 4 minimum energy curves, M of H, for torus knots in their simplest configuration. The minima is at H equals non-zero, off zero, because each of these knots is chiral in character. Of course, one has to decide, well, you can take any arbitrary H by simply cutting and twisting the knot and injecting twist in the interior. Well, these are actually equivalent tight knots, known as tight knots in much of the literature, defined in a purely geometrical way. This is from a paper by Cantarella, a recent 2014 paper, which shows the interesting phenomenon for the torus knot T25. Here's the equivalent torus knot T52. They're the same knot, but different, again, initial configurations. And the equivalent of the energy here in terms of a normalized length of the knot, for 48.23 here, considerably greater for the more complex initial configuration. But the interesting phenomenon shown here is that for a configuration that breaks both symmetries, the energy is actually slightly less than the energy for the twofold symmetry. Here it may be a coincidence, but the T25 here, if we take the minimum energy for H equals about 8, the minimum energy, if I go along here, is very close to the 48.23 found by Cantarella, but I'm not sure this may be just coincidence. This is a paper by Patil et al. Very recently put on the archive just about 2 weeks ago. So I just comment that the subject is advancing rapidly. 14 different knots shown here, and the minimum energy states computed for different values of the helicity. here the simplest trefoil knot, and again showing the minimum helicity according to this, the minimum energy according to the color scale here, off center, and moving rather differently in the two directions as helicity changes. Now, a few comments about the finite time singularity problem, if time permits. This is famous, one of the Clay problems. Given an initially smooth, localized velocity field of finite energy in an incompressible space-filling fluid of arbitrarily small viscosity, can a singularity of the field appear within a finite time under Navier-Stokes evolution? Yoshi Kimura and I have studied it by looking at this particular initial configuration of two vorticity. These are flux tubes of vorticity. So vortex rings, essentially, each one tending to propagate towards the plane of symmetry. But what happens here when the two are very near each other is that each one locally moves the other one upwards. So they're distorted upwards locally. And here I think I can show you what happens. According to Biot-Savart law, very near these points here, the arrows on these curves show the velocity, which is increasing, and the two curves are approaching each other. Note that the curvature increases. I can move this along. See the increasing curvature and the decreasing separation, the increasing velocity, and we let it go here, and it seems to become singular, certainly at a finite time. Well, this is the phenomenon that we sought to analyze, taking account of the finite cross-section with a Gaussian profile of vorticity across the cross-section. Well, it's as if the vortex rings, which are shown in blue here, they're propagating towards the vertex of a pyramid. And they reconnect, and reconnected strands, shown here in red, then propagate away from the vertex of the pyramid. So that's what we describe as pyramid reconnection. And again, it's shown rather differently here, but looked at from a different angle. The velocities increase and become singular at a finite time. These were earlier references which we studied this problem. Well, we reduced this problem to a dynamical system for the separation at this point here, the separation of the two vortex tubes, the curvature, which is increasing, and the cross-section measured by delta. It's more conveniently put as an equation for delta squared. There is a small parameter, epsilon, which is the inverse of the vortex Reynolds number. And there's a parameter gamma, which represents the proportion of the initial vorticity which has reconnected. Well, we have an equation for gamma that we derive, but alas, this equation seriously underestimates the rate of reconnection. And this is demonstrated by direct numerical simulation by Yao and Hussein in this paper. So we've got this wrong, and this equation is the one that misrepresents the reconnection process. However, if we brutally go ahead and integrate these equations numerically, then I've done this here for R gamma equal 10 to the 5, so epsilon would be 10 to the minus 5. The gamma remains approximately equal to unity. In other words, before reconnection even begins, the scale of the cross-section appears to go to 0, and the maximum vorticity, which is actually gamma divided by delta squared, appears to, well, become very large, an incipient singularity at sufficiently large R gamma. But we don't know if this is real. The problem is that DNS will not get you to sufficiently high R gamma, and really we want to be in the asymptotic regime where R gamma goes to infinity before we can know whether a singularity really occurs or not. Well, a few outstanding questions. For a given forcing by, for example, a rotating cylinder in this corner flow problem, if we increase the Reynolds number to ideally large Reynolds number, then how does the position of these initial separation and reconnection points change, and how does the whole flow pattern change with increasing Reynolds number? Secondly, for flow of water, a stream of water into a bath, or you can even show this by pouring water into a glass of water. For a small flow rate, it's very silent and there are no bubbles, but at a critical flow rate, bubbles appear, and they appear, I believe, through entrainment through the cusp, which would be a roughly circular cusp. But it's like the two-dimensional problem, but again, actually a high Reynolds number problem here. But I think the behavior in the immediate vicinity of the cusp is generic and locally low Reynolds number, and that's where the bubbles get into the fluid. So what's the critical flow rate at which these are entrained? Third problem is this flow that I described, the chaotic flow inside a sphere, is it capable of dynamo action? This is something that we're already working on, and I think the answer is going to be certainly yes. But alternatively, the complementary problem, if we think of that as an initial magnetic field, not a flow, but a field, to what would it relax in a perfectly conducting viscous fluid? That's an extremely difficult problem because it's a chaotic field which wants to relax, but it doesn't quite know what to relax to. Difficult. Lastly, well, there are many other problems, but this finite time singularity, yes or no, solve this, and I would say that you can then retire in peace. Any questions on any of these issues?
Yeah, Keith DeWitt Sumner's here with a question. My question is that with your pyramid reconnection, you've got these blue vortex tubes. That's an antiparallel reconnection that occurs at a point or along an arc on the vortex. It's at a point rather than along an arc on the tubes.
I believe it occurs at a point, yes. Of course, direct numerical simulation shows a more distributed form of reconnection, but that, of course, is at very finite vortex Reynolds number, and we really still don't know what happens when the Reynolds number becomes very, very much larger.
Okay, interesting, yeah.
So
I have a question related to what DeWitt was asking. Do you, in your particular case, you keep a cross section, however small, circular, or gets deformed to an ellipse?
We do. We assume it. We assume the cross section remains circular, and with Gaussian, there are reasons for that assumption. Now, in fact, that's probably the reason that during reconnection, I'm sure it is one of the reasons, during reconnection, it certainly does not remain circular. In fact, we know that there's a tendency to shed vorticity into a tail. It becomes a sort of head-tail configuration, and therefore the reconnection becomes very much accelerated because of this. That is something that we're now trying to work on to improve the description.
Surely you I know it's very, very difficult problem. Do you remember, I'm sure, the fact that we have also these bridging filamentary structures that are draining out some vorticity. And so this probably has to do with this squeezing of the elliptical cross-section during reconnection, during the last processes of reconnection.
I think you're right. There is a sort of filamentary shedding. That is that shedding into the tail, which does occur here. I mean, certainly if you do a 2D model of two vortices propagating along and force them to come together by a straining flow, then you get this same sort of shedding into a tail, a long tail. So that is something that has to be incorporated into the 3D reconnection. It is very difficult, as you point out. I think it's a problem. It's a current problem. A lot of people, of course, are very keen to solve this type of problem.